All right, so this is my first reaction video to a physicist working a problem. So let's see how this goes. This is Rhett Allain, just posted this today. I put him on double speed though so that we can get to the action fast.
Okay, so here's the problem. I have this mass on a frictionless table, and I push it up against the spring and let go. And I want to find out how fast it's going when it stops. And it's not connected to the spring. So once it gets up back to the point where it started.
So he says it's not connected to the spring, so it's not going to just bounce back and around again. So I thought that was really important for him to say. I'm curious though if he's going to expect the spring to like overshoot. You know, if you compress a spring, does it overshoot past this line? That's a really interesting question.
The spring stops, pushing on it, and the thing just flies off. It doesn't really matter actually either way. The solution's the same. So the question is how fast is it going? And I picked some values here. The mass is 0.01 kilograms. The spring constant is 12 newtons per meter. Actually, I don't need this natural length the way I did this. I called this x equals 0, and that's it. It starts here at x equals negative 0.03. That's how far it got compressed. That's the unstretched line. So in the first way you should think about this problem is say, look.
So I thought it was interesting that he actually has this value here and then ended up saying right away he wasn't going to need it. I think that it was really interesting because he could have just sort of plowed forward and later said, wow, it turns out I didn't need this. So it shows that he's kind of worked this problem a little bit, put some thought into it. But at some point he kind of changed his mind as to whether this was a useful thing. And then he talks about sort of how he's drawn it and how he's sort of defined these numbers.
Look, I have a position and a position, and I don't really care about when it happened. I just care about the speed. And if I just care about the positions and speed, that should trigger in your mind to say, hey, I'm going to use work energy. So here's the work energy principle. It says work is a change in energy. And now, once I write that down, the next thing I need to do is say, what is my system? So my system in this case is going to be equal to the mass plus the spring. Since this...
I really liked how he said that, you know, because he's doing work energy, that the system was a really important part. So right away, he's just being absolutely clear about that.
Spring is in the system, then the spring is not going to do work on the system. That means that there will be a spring potential energy. So I'm going to have this work is the change in kinetic energy of the mass plus a change in spring potential energy of the spring. Now, that's my whole system. There is a gravitational force and a normal force pushing on this, but if I look at that right here, here's my mass, and here's the displacement delta R, there's mg, there's the normal force. Both of those are perpendicular to the displacement. Work equals F dot delta R. Since they're perpendicular, the work done by these two forces is 0. So I get 0 equals the change in kinetic energy plus a change in spring potential.
I think that's a really interesting way to talk about how the vertical doesn't matter, right? He could have just said, vertical doesn't matter, let's get moving. But he actually talks about this dot product and how that's actually the important reason for why we can kind of focus on the horizontal. So I think that's really cool.
Now we define kinetic energy as 1/2 mv squared, and potential energy, spring potential energy, is 1/2 k s squared, where s is the amount is stretched or compressed. So let's write this out.
So it's funny that he has X, L, and now S here. So I thought that was really, oh, and he has R too. So lots and lots of different ways to talk about distance or displacement. And obviously he's about to sort of figure out that the X1 is going to be plugged in here directly. And that's why sort of the negative sign I think is going to be of interest here in a little bit.
I'm going to call this position 1 and this position 2. So 0 equals K2 minus K1, that's final kinetic energy minus initial kinetic energy, plus U2 minus U1. Now, 2 of these terms are 0, because since the velocity...
Come on. Every time you write this, you have to mention the band. Come on!
Since the kinetic energy depends on the velocity, if I push this back and release it from rest, it has 0 velocity right here. That means the initial kinetic energy is 0. And the same is true for the spring. Right here, the spring is compressed, so there's energy stored in the potential energy in the spring. Right here, the spring is not compressed, so there is no potential energy there. So U2 is 0. So I get K2 minus U1 equals 0, or K2 equals U1. So now I just need to put in my values. 1/2 m v2 squared equals 1/2 k s squared. S1, s is going to be this distance. If this is at x equals 0 and I push it back to negative 0.03, this is going to be, let's just call it s, but s is 0.03. Now I can solve for v. I can multiply both sides by 2. I can divide both sides by m. And I get v2 equals the square root of k s squared over m. Let's put in my values. So it's going to be...
That's interesting to me to put the s squared in here. You know, some people would have done the square root of this right away and put the s out here and maybe been able to make a comment quickly that the speed is going to be directly linearly proportional to how much you crunch the spring. He's got it in here. My guess is he's about to sort of show that simplification. He talks about 2 methods. There's no question he's doing the easier method first, because I'm guessing he's going to have to do some integral of force here in a little while. I think I would have done it in the other order. So I'm curious to see why he did it in this order.
The square root of 12 times 0.03 squared divided by 0.01. I haven't used my calculator in a while, so let's crank out the calculator. Turn on. There we go. Okay.
Okay, let's pause here for a second. What is going on up here? Okay, well, we'll just let him keep going here.
So I'm going to put in 12, enter, 0.03, and then I'm going to square that, and then I'm going to multiply by the 12. Now I'm going to divide by 0.01. Oh, and I lost the battery. Stay. Okay. So let's try it again. 12, enter, 0.03 squared times 0.01 divided by, and then take the square root, and I get 1.04 meters per second. That's my velocity. Okay, let's do it again. Same problem.
More digits of precision.
Use momentum principle. Okay, cool. I'm cool with
Than
that.
he
So
had.
picture again right here. Here is the compressed spring.
I'll say that after pausing. So his answer had more digits of precision than any of the numbers that he put in there. You know me, I don't care about any of that crap, but I know that some chemistry professors are freaking out right now.
So there's position 1, position 2. It's going that way. Okay. So now I'm going to say the momentum principle, F net, is the change in momentum over the change in time. In the x direction, let's call this the x direction. Then I can just say F net x equals delta p x over delta t. Now, I know the initial momentum. Momentum is defined as px is going to be mvx. So I know the initial momentum is 0. And I want to find the final momentum. Okay.
All right, so I'm gonna jump ahead here because I'm really curious about how much integration that he has to do. Is just in the top of my head, I was thinking since the force is changing over time. Let's see. Oh, okay. Nope, he's doing it a little bit differently. Very interesting. Cruising ahead here. Come on. So then he does the Python. Okay, so let's back up. Let's let him finish up what he's up to here. So basically what he's saying, yeah, okay, we have to know what force is going into it, and we know that that's a function of position, so this is a little bit nasty, and then he's going to jump into the Python. So very interesting. Let's see how he does it.
Equals x1 plus p2 over m delta t. And then now I know where it is after 0.001 seconds. It's probably not over here yet, but I have an estimate. Now I can find t2 is going to be equal to t1, which is, let's say, 0, plus delta t. Now I can do it all again. Now I can do it for the next 0.01 seconds, and go back up here and calculate t3 based on t2, and then calculate x3.
I mean, this is an interesting choice. It's a really, really small amount of time.
Which is at x equals 0, and then I can find final velocity. And that's what I'm going to do. You can do this with your calculator.
Yeah, so I thought he was going to do the integral. I didn't realize he was setting this up for a Python computation. So very, very interesting. He's talking about baby steps where there's no big changes to the force. And so if you have constant force, this stuff is really easy. But crud, when it goes to different positions of the spring, it's going to have different forces. Ugh. But as long as you do it in tiny little baby steps, then it's fine. And I'm guessing he's going to say that on the computer doesn't care about doing baby steps. It'll do it all day long. So let's keep going.
A whole bunch of steps. If I want this to go for 1 second, I have to do all these calculations 1,000 times. Probably less than a second. Okay. But even if it's like half a second, that's still 500 calculations. That's a lot. I don't want to do that. I'm going to make something else do it. I'm going to make the computer do it. You know what?
Awesome.
So let's scoot on over to the computer and do this calculation.
Okay, I like that. Okay.
Okay, so here we are. Welcome over to my computer. And I've already started. I started without you. All I did was enter in the mass and spring constant and initial position. So now we just need to implement what exactly we said we were going to do. So I do need a couple more things. The first thing I need is I'm going to go up here and call.
I know that Rhett really loves to use Trinket for all of these things, and I think it's because he's super excited about VPython, which is going to eventually be able to maybe make a pretty picture. But it's interesting, if you're just doing a calculation, VPython is super overkill. And so I wonder about sort of what choices people would make, right? So I would probably not throw this in Trinket myself. It's not my go-to. If I'm doing Python, I would probably use something else. But there's no question that he's going to make a pretty cool. He could make a pretty cool visualization of this if he wanted to by jumping into Trinket and using VPython.
This just x. I don't need to call x1. I'm going to keep changing that. It doesn't really matter. I do need the initial momentum, so I'm going to say p equals 0. One thing you'll notice in here, this is a numerical calculation. It uses numbers. You don't put the units in. If you want to include the units in Python, you can put a little comment here. The number sign, everything after the number sign is a comment. So kilograms comment, newtons per meter, meters.
So when I'm doing that kind of thing, I like to talk to my students about how, as long as you use this sort of fundamental base unit of things, so seconds, kilograms, meters, newtons, your answer is also going to be a fundamental unit, right? And so if you're going for speed, you know that if you do this appropriately, use the 4 or 5 standard metric units, your answer will be in meters per second. So I think that's a really interesting thing to remind students of.
And this would be kilogram meters per second. Okay, and then I need t equals 0, dt, where I said was 0.001. Now, I need to make these calculations in a loop, and so I'm just going to say while t is less than a half, I'm going to do a half a second. I'm just picking something. Okay, so I put the colon there. I'm not going to plot or make anything, I'm just going to show it, so it doesn't really matter. So the first thing I need to do is I'm going to separate this into another stuff. I'm going to first calculate the force. So F equals negative k times x. So this will give a positive force, and force in the positive direction because x is negative. Now I'm going to use that to update the momentum. P equals p plus f times delta dt. Now you'll notice something weird here, and that's that I have p on both sides of the equation because this is not an algebraic equation. This is a make equal to equation. This says take the momentum, which is 0, calculate this f delta t and add it, and then make that the new momentum. So I don't have to worry about p1, p2, p3, p4, all that stuff. It's just p.
Yeah.
You change p. Now I'm going
Interesting.
to update the position, x
Useful.
equals x plus p times dt divided by m.
Same thing
Now I'm
again.
going to update time, t equals t plus dt. Now I want to print out the final velocity, so I'm going to say print v equals p divided by m, and I will give units here because I don't want to be a barbarian, right? And let's print out the position.
I love that in the print statement that you can actually do one more calculation, right? So in other programming languages, you would have had to make a variable called p and set it equal to p over m, because there's some programming languages that really don't want to do additional calculations inside of commands like this. That's why Python is so cool. One of the many reasons.
Position 2, because we want it at x equals 0. X equals x meters. And I'm going to run it. And you notice, oh, actually, that's pretty close. I'm pretty close to, wow, that was a good guess there, huh? I'm pretty close to x equals 0, but not quite. I can adjust this. It looks like it didn't go quite far enough. So let's just run this for 5.1 seconds and see what happens. And it's...
So that's really, really interesting. He doesn't know how long this takes, and he's trying to get this back up to 0. So when it would let go of the spring again. So I'm curious to see what he does with that. That's really interesting.
Maybe, is that a little bit closer? Let's say 511. 0.01. No, that's too far. Let's do 0.05. That's right. Okay, that's pretty close. Okay, and let's just go down here, and I remember the equation for the calculated b, so I'll say b calc is equal to the square root of k times
Oh, I really love this, being able to show the comparison. Very smart.
s squared divided by m. I think that's what it was. Yeah. And so now we go up here and say s equals 0.03, and now I'm going to print that, just for comparison. B calc equals b calc meters per second. Run it.
So right there, right, he could have put this equation right here. So it's sort of interesting that he has both versions of what I was just talking about here.
Okay, so I get, so that is negative. I'm actually going too long of a time. Actually, you can see what happened here. It went all the way, it's oscillating, and went all the way to the farthest point and came back, so the time is way too long. Okay, that's fine. Let's do this another way. Let's, instead of doing it for a time, let's say, while...
Wow, what a really cool thing. I mean, it didn't freak him out. He's like, oh, it's negative. Oh, I get what happened. He's thinking ahead. He knows that it's oscillating. He could have stopped and said, well, let me draw you a picture of that. But he's going to dramatically reduce his time to show how it works.
x is less than or equal to 0. Because it starts off negative. Once it gets to 0, it stops. Okay, and then I'm going to print out the time, too, because...
Super smart. A much smarter way to do it. Awesome.
I want to know how far off I was. T equals t seconds. Right. And look at that. There's my numerical calculation.
Gorgeous, gorgeous. All right, I'm going to bring this to a close. Rhett, fantastic job. I thought there was a really, really interesting things going on, and thank you for letting me try out this approach. I hope people find it entertaining.